once you have a substituted benzene, in other words, once you already have a substituent on the benzene itself, the reactivity of the benzene changes. That substituent is going to direct where the next substituent will go, such as if you're doing more than one, adding more than one substituent onto the benzene ring. Okay, so if you recall, this is the nucleophile. The nucleophile comes and grabs whatever electrophile that we just produced, and this is the first step. Okay, so if you increase the nucleophilicity of the benzene, that's going to increase the reaction speed. Let me rephrase that. If you activate that benzene ring by adding electron density into the ring, this reaction will happen more easily. It ends up stabilizing that positive charge. On the other hand, if you deactivate or pull electron density out of the center of that ring, it's not going to react as quickly with an electron because it has less negative charge, being the electrons in the center, to stabilize out that positive charge that's right there. Okay, so we have two major categories of the effects and how they can change the nucleophilicity or the amount of electron density within the benzene ring. The first is an inductive effect. You all actually know what inductive effects are before. So these are things that sort of pull electrons just because you have electronegative atoms, and that's going to change the electronegativity of the benzene due to it just pulling some electrons in a particular area towards the electron negative atoms. One thing you may not be aware of is the alkyl group. So that's like any R group. You've got specifically any R group that's made of carbon chains, pushes electrons into the benzene ring by what we call hyperconjugation, which is a technical term, but don't worry about that too much, except that the inductive effects push and pull electrons through space, and we've talked about those before. They still happen. The resonance effects, on the other hand, are really, really, really important. And they do play into account with the inductive effects, but the reality is that resonance is the most important of these categories anyway. So if we look at a particular type of substituent that will donate electrons into the ring, such as this NH2 here, note that we could have the electrons come down and down, making this resonance structure. I want to point something out here. As I do this, I never change the electron count so that it's less than 8 on any of the atoms that are involved. This has 8, 8, and 8, and again it has 8, 8, and 8. Okay. Again, you can change these electrons around, push them around the ring so that they become negative here, then it goes to the para position. And then as we move these back, that's going to go back to the ortho position. So we have two ortho positions and a para position where that negative charge can reside in the in the resonance structures here. On the other hand, if you have a case such as this, where electrons cannot be pushed into the ring, notice that if you, how could you do that? That just really won't work and still give everybody 8 electrons. And you may say, oh, well, great, take that and push it down. But if you take this bond right there and push it down into that carbon, you just left oxygen with 6 electrons. That is way too high of an energy state because that's just way too much unhappiness for that oxygen. So the reality is that these electrons, the only way to form a real resonance structure, have to come up to the carbon, allowing these electrons in that double bond to go to the oxygen. Notice again, we've got 8 electrons on that oxygen, here and here. Carbon still has 8. Now, yes, it is the case, in this particular case, carbon only has 3 bonds. That means that it's deficient some. It can hold that positive charge. Oxygen, not so much. So, we can go through resonance structures and determine what it is that that's going to look like. And there we go. So notice here that our charges in either case end up in the ortho and para positions pretty much exclusively. That's really important. Okay, so here's what I want you to try to do. Let's try both phenol and nitrobenzene and determine what those resonance structures are going to be, first of all. I want you to pause the video and attempt that on your own. And when you're ready, let's move on. Okay. So here's what's going to happen with phenol. Your electrons are going to come down, over, and then you get the negative charge in the ortho and para positions. This gives rise to a hybrid that looks sort of like that. In other words, you've got sort of a partial negative charge right here at the ortho and para positions. They're all equal. So if you are an electrophile and you happen to be attracted to that opposite sign over there, then you're going to want to attack either there or there. In other words, the fact that this OH is on there tells this electrophile where to go next. This is what we refer to as an ortho-para directing substituent. Okay. Now, if you looked at the nitro group, here's what he looks like. We've got positive charges here, here, and here, which means that his hybrid looks sort of like this. Okay, well now we've got a positive charge. He doesn't really want to go over there, does he? There's not a negative over there. He wants to go someplace where there is more electron density. But unfortunately, there's not really a whole bunch of electron density because it's all sucked up upstairs. Which means that this is a deactivating substituent. It makes that nucleophile less electron rich. Therefore, this reaction just won't happen as quickly as what it could otherwise. And he's certainly not going to go sit on top of a positive charge. So the place that he ends up going is actually where there's not a positive charge already. So here and here. In other words, to the meta positions there. So we have moderate and strong deactivating substituents. Those guys are going to direct to a meta position. Okay, there's also a group of weakly deactivating halogens here, and I'll get to that list in just a moment. They can also resonate, even though it would lead a positive charge on the halogen itself, and they can put electrons into the ring technically. Even though inductively they're really deactivating, the resonance is going to win, and they're going to still be ortho-para directors, though they're not really too happy about it. Okay, so here's what I mean by this list. This is a list that if you plan on doing any synthesis ever, you have to know. You've just got to memorize it. There's no other way to get about doing this. Well, really and truly, I don't memorize it. I understand it. I would much rather go through and understand how to go through and make these resonance structures and go, okay, all you really need to identify is the first step. Go, okay, well, this is going to put electrons into the ring, and in this case, it's going to pull electrons out of the ring. Oh, I'm sorry, I never drew that up there. Okay. So, in this case, these guys are what we refer to as strongly activating substituents. The strongly activating substituents are the ones that are going to donate electrons into the ring very easily. Moderately activating will relatively donate the electrons in pretty easily. The weakly activating are inductively pushing electrons in, and the weakly deactivating are the halogens that I just talked about. There's going to be a weird line in the sand that's going to form right here. So it's right at the weakly deactivating list. In other words, includes the R groups and the halogens. These guys are ortho paradirectors. So if you have one of these substituents on a benzene and you try to put something else on that benzene through an EAS reaction, then these are going to direct that next substituent to the ortho or para position. And yes, you end up with both products. You'll end up with a little bit more ortho just because of the fact that there's two of those and one of the para. The moderately and strongly deactivating substituents. Note that these include positive charges here, because once you occupy the lone pairs of a nitrogen, you certainly can't resonate them into a ring. NO2 is deactivating because it's got 4 bonds on the nitrogen, SO3H, and the CN. Okay, so these guys are going to be metadirectors. Again, you need to know these, or at least be able to rationalize your way through them. Halogens and R groups are pretty easy. Those are orthopara-directors. Okay, there are some exceptions to the rules that we talked about over the last couple of lessons here. When you have strong activators, don't use iron because you're going to get a lot of stuff on there. So NH2 with FeB, R3 and Br2 will actually give you 3 brominations very quickly. You can't even control it, so it's not as if you can control how much you are even adding to the reaction mixture. It's so strong of an activator to have an NH2. You can just add Br2 and you'll get both your ortho and para products. So this is what I mean, like it's an ortho para director. I've got a substituent on here, I'm adding a bromine, and that's going to give me both the ortho and the para products. When we do Friedel-Crafts, acylation and alkylation, that's not going to work well with anything deactivating, but the strongly deactivating really is not going to work very well. They also don't work with any nitrogen attached to the ring. So be very wary of using that. A lot of times what you find is that you just got to go through and put a BR on there and then maybe replace it. This guy's explosive, so we actually just have to add a protection group on that nitrogen before you even go through the process of adding HNO3 and H2SO4. So there are some exceptions. There's always exceptions, and that's why we can't say that word always, because it's a really bad word, because it can lie to you. Okay, see you soon.